All right, let's get started for today. Can you all hear me?
Yep, Neri.
Excellent. The videos from the last two classes are up. I apologize. We had a bit of a dumpster fire, so I got sidetracked and forgot about them, but they've been put up now. Any questions about anything before I start? Assignment 3 is due midnight tonight. I'll check with Cornelia to see how we're going to mark that. And actually, today and Friday are the last two classes of the semester. So we're going to finish up Hadoop today, and we're going to start talking about Neo4j, and we'll finish off Neo4j on Friday. So
I have one quick question about the assignment.
sure.
I think it's pretty obvious. There's a bunch of intermediate files that you're going to make as before you merge into the final sorted thing.
Mm-hmm.
We are not supposed to clean up those files, correct?
No, please don't, because actually,
Okay.
yeah, what we're doing is we're doing diffs on the intermediate and the final results to see if things are coming out the way we expect them to, and if they're not, where they're not. And so definitely don't clean them up. Yeah, we need them.
That's what I figured. I just got bitten on the last assignment because I forgot to clean up some files. So I just didn't want to make the same mistake twice.
Okay, that shouldn't have happened. Send me an email about that, because cleaning up files, like, oh, I see what you're talking about. Yeah, so on the last,
I missed the one note because the font was kind of small and I just didn't read it quite carefully enough. It said,
yeah, on the last assignment we did have you clean up files unless we said not to, because there was some follow-on. But on this one, definitely don't clean them up. We're gonna use them.
I missed that one note. It worked on everything else. Didn't want that to happen twice. Thanks.
Yeah, no, you're good. You're doing what you need to do. Any other questions about the assignment? All right, so let's finish up with Hive, which is the second language we're going to talk about related to Hadoop. So once you have your data warehouse, and so in our example, via Higgs cleaning and transforming, Hive, which was developed at Facebook in 2008, is used to assign structure to data and query using something called HiveQL, which is basically like SQL. So Hive uses HiveQL to query data on a Hadoop cluster. So this idea of data warehouse has been around for a long time, and it's, I guess its definition sort of varies a little bit depending on who you're talking about. But here, the difference between data and data warehouse would be that data is raw data. So data coming in directly from some source, sensors, data sets that are being collected by someone that you're actually pulling in. And then a data warehouse, in theory, is supposed to be that data after it's been cleaned, transformed, after you've done whatever you need to do to it to get it into a format that you can actually use to solve tasks that you want to solve. And so what HiveQL does is it allows you to take that data and structure it in a way so that you can do efficient query retrieval and other operations. Okay. Now, not all data warehouses work like this, unfortunately. So what you find in the real world is that what people call a data warehouse is often the actual raw data that's been pulled in and just stored in some arbitrary format into some storage cluster. And so you don't really have that cleaning and transforming. That's actually done as data comes out of the data warehouse. But in Hadoop type terminology, the idea is that no, a data warehouse that you're actually querying with Hive has been set up to be ready to go. And so there's no additional, what you would call data cleaning steps that are required to actually use it. So if only all data warehouses were like that, it would be wonderful, but they aren't. So HiveQL is designed to mimic query portions of SQL or SQL. So it's declarative. And declarative means you say what you want to do and then the system does it for you, as opposed to procedural where you actually describe how you want it, how to do what you want to do, and then it does it for you. Okay. So with a declarative language, you get less control over how the operation occurs, okay, in general. And HiveQL optimizes, the HiveQL, optimizer converts a query into MapReduce jobs. So it's very similar to the way that Pig works. So you have this high-level language. Even Pig was SQLite, but here you have a high-level language that's more SQLite, and so you issue SQLite queries. And so from the point of view of someone who already knows how to work in a RDMS, Relational Database Management System, it doesn't seem that different, but what's happening is in the background, because you're running on a Hadoop cluster, the HiveQL optimizer is actually trying to convert everything into MapReduce jobs so that these queries can run much more quickly. And so that's the basic idea, is maintain familiarity with an existing language that many people know, but provide all the advanced functionality and efficiencies that Hadoop is going to provide in terms of the size of data that it can store and the speed with which it can actually work on that data. And other things like you know, replication, fault tolerance, et cetera, et cetera, et cetera. Okay. So Hive data is structured into tables that are similar to a relational database management system. So an explicit schema describes a table's columns. So like any RDBMS, if you've used Postgres, SQL, or trying to think of the name of we've got an open source version now of MySQL that I'm using because everyone's afraid that Oracle is going to somehow screw us at some point since they now own MySQL. Anyway, MySQL. So any database, any relational database management system, the first thing you have to do is actually define the columns and say what are they, and so that's sort of locked in, that's the schema. You have to do the same thing in HiveQL. And then each table can be partitioned or sliced based on one or more of its columns. So you might say something like create table. Looks very similar, right, if you know SQL. We're going to call it movie. And then we're going to say it has an ID, which is an integer, and a name, which is, in this case, a string. You don't specify some maximum length string. And then a duration, which is an integer as well. And then you can actually partition by some year, which is an int. Okay. So any fields inside this partition by block are also considered to be columns inside the database. They're just columns that you can partition on. Okay. So this is also a column in the database schema. Okay, but it's a special column, partition column. Okay. So why do you want to partition? Partitioning is how you're telling Hadoop how you want to distribute data over the cluster. Okay. So you do have control over how slices and what do they call them? Cluster blocks and other things are created. So partitioning is to efficiently distribute data over the cluster. So each partition value or it could be a value tuple. It depends on, I think, what Hadoop decides. Creates a separate subdirectory to hold records with the given value or values. Okay. And when queries filter the data, that's what a query does, right? A query basically takes the entire data set and then returns some subset of it, so it's performing a filter on the data. E.g. with a, say, where clause. Only those subdirectories that match the filter need to be processed. So obviously that can significantly improve performance. Now the responsibility on your part is that those columns that you choose to partition by should be columns that you're actually going to be using as filtering columns often in your queries, right? So just like when we talked about secondary key indices, we said there's no point making a secondary key index if you're never going to actually ask to filter by that index. It's just a waste of time. So you shouldn't be partitioning on columns that you don't expect to actually have involved in selections through a query, because then you've just created a bunch of subdirectories, but they're always all going to be involved in a query, and so you haven't saved anything. You've probably made it actually a little bit more complicated for the system to do whatever you're asking it to do. So the expectation in our example is that we're going to do a lot of queries where we're going to say that the year falls within some particular year or range of years, and that's why we actually created a partitioning on year. Okay. Now, alternatively, HiveQL can subdivide data into buckets. And this is also for optimization. And it's done by hashing values for a target column. So that would be your quote unquote key value, your key column. Okay. And distributing hash values over a user chosen number of buckets. So you can say again something like create table, movie, and it's going to have the same stuff in it that it did before, an int ID, a string name, and then an integer duration. And you can partition by final column int year, so that's all the same as before. But then you can say clustered by name into 20 buckets. Okay. So what you've defined is you define name to be, in essence, a key, and every time you do a query, the name is going to be hashed, and a particular bucket is going to be accessed to try to find the movie with that particular name. Okay. And again, this is for efficiency, so that you can cut down on the number of buckets that you need to actually consider, because again, the assumption is that you're going to be doing queries that involve specific names of movies, and so there's some advantage to doing this hashing. So here, the movie's name is converted into a hash value, and on the range, in our case, it was 0 through 19. Okay. And so the resulting 20 buckets are stored on the HDFS cluster in a way that supports efficient retrieval of individual buckets. Which makes sense, because once you ask for a particular movie, its name hashes to some bucket, and so you want to be able to grab a particular bucket efficiently. All right, and so I don't know the exact algorithm that Hive is using to do this, but I assume that it's something to do with how it's storing its blocks and their locality. Okay. So the blocks that make a particular bucket. Okay. And again, I haven't looked at the particular Hive algorithm, but my suspicion or my experience is that you remember we have that partition by year, and that was done so that when you do queries that involve year or your range of years, you can do something efficient. So I actually think that that subdirectory scheme is done for each bucket. So your expectation is that first you're going to get to a bucket based on a name, and then once you're in that bucket, you're going to look at certain subdirectories related to that bucket based on the partition columns, which in our example are year. And so there's a double attempt to try to improve efficiency when it's doing this. So just in summary of this, I'm not going to say much more about Hive or Pig, but the idea is that you first start with Pig for your ETL, your extraction, transform, load pipeline. And you produce tables that Hive can use for report generation or exploratory queries. And that's not any different from any other type of raw data cleaning and then analytics that's done on the clean data. It's just that in this case, Pig and Hive run on top of a Hadoop cluster, and so in theory, they're supposed to be running faster. Okay. So you might wonder, well, what if I want to write a MapReduce job directly and I don't want to use one of these intermediate languages to do that? You can do that. So normally, I'll call them raw MapReduce jobs can be written in Java. That's the language that they normally suggest, although it's not the only language. You can do this in a variety of languages. And so the difference is that Java MapReduce jobs usually run faster. Not surprising, because you're in complete control of how that job executes, so you can optimize it for the particular job that you're trying to run. But Pig and Hive programs are usually quicker and more efficient to implement. So if it's just you and you know MapReduce really well and you know Java really well, you're probably never going to use Pig and Hive, or you might choose not to. But in some larger corporation where a lot of the programmers don't really know anything about Hadoop or HDFS or MapReduce or anything like that, but they do know some SQL, then Pig and Hive are a great choice for them because they can work in something that's fairly familiar. They're going to get most of the advantages of running on a large cluster with replication so that they can do MapReduce, but they don't ever need to know anything about MapReduce. They just know that their jobs run a little bit faster than they would if they were run sequentially. Okay. Yeah. And these continue to be used by the companies that have developed them, although they're continuing to update them, obviously. And so they've proven to be fairly useful, fairly long-lived, which isn't always the case with a lot of these languages. So before I move on to NoSQL and Neo4j, are there any questions about this?
So this is also probably another slightly tangential question. At what point do you, or is there really like a threshold to go from, say, a really beefed up RDBMS, right? And then rather going to like a big data warehouse? Because I feel like there's an interesting thing there that, let's say you're in the realm of a couple 100 million records or something in an RDBMS table, and then you start to scale something and suddenly you have close to 1 billion. Well, maybe at that point you should have moved to a data warehouse, but it's like that weird thing, like now that you have it in there, you've probably figured out how to do it in an RDBMS way pretty efficiently to support that use case. So do you keep it there? That's like more an implementation question. I just didn't know if you had seen good thresholds or ideas for when you should start migrating to something more data warehouse-y for big data-y things.
Sure.
Super broad question.
And so I think in general what happens is that the decision about whether you're going to use a traditional relational database or whether you're going to use some sort of more sophisticated cluster-like strategy like Hadoop is actually made very early in the design phase. It's much less likely that you're going to transition at some point in the future because, as you say, the transition cost is really high, and so there would have to be a pretty big return on your investment if you were going to do that. Okay. And of course, the RDBMS, the relational database people aren't just sitting around watching Hadoop eat their lunch. They now support the ability to run relational databases that don't fit in main memory, that are replicated, that have fault tolerance. They've actually already always had fault tolerance to their operation logs and other things like that. So part of the decision may come down to whether you think that the kinds of things you're going to do on your data are easily parallelizable. If that's the case, then you're probably from the get-go going to use Hadoop, because it's not an issue for you of size necessarily. It's an issue of, well, it's really easy to run something in MapReduce on Hadoop using either direct MapReduce or PigHive. But in a relational database system, that's not the case at all. Or it may be the other way around. You may actually realize, like, I'm never going to parallelize any of this. And so the relational database management system is going to be a lot faster, more efficient probably, to do just general RDBMS, relational database queries, because RDBMS are based on relational algebra. And so there is mathematical certainty behind what you're doing there. And so that's almost always the case for any practical company. I think I told you this, so when I did some work many years ago for one of the life insurance companies, they were using IBM mainframes in PL1. Okay. And I think they're probably still using IBM mainframes in PL1. They may have other languages that they've adopted to do new projects, but the existing projects that they have will never be converted to any other language, because the cost and danger of doing that is too big, basically. And it works. PL1 actually does everything they need to do. It's a great sort of reporting, pipelining, data manipulation language. If you couple it together with JCL, job control language, between the PL1 programs. And so the same thing I suspect would be the case for Hadoop versus RDBMS. And I don't know if we'll get into this discussion, but one of the things that happened when NoSQL came along, and we'll talk about what that means, is that everybody thought, yeah, I'm going to use NoSQL. You know, this is going to be great. And some people even thought hard about why it might be a good idea to do that instead of just doing it because it was a buzzword. And there are some very interesting stories of catastrophic failure because they really needed a relational database and they had to convert everything over to RDBMS some point down the line, and it was incredibly expensive. And what they said was, we just didn't think very hard about this. And so we just went for the sort of hot tamale at the time, and it turned out to be a very bad choice. And so I don't think relational databases are going anywhere. There are certainly use cases for things like graphs, like unstructured text, which is sort of a funny misnomer, but anyway, where yes, you might want to use Mongo, you might want to use Neo4j, but they're not replacements for Oracle or Microsoft SQL Server. They're just almost niche products that are designed for very particular things, and they do that one thing very well. And if that's what you're going to be doing, if that's all you're going to be doing, or that's mostly what you're going to be doing, then yeah, you should go with one of those. So I don't know if that answers the question or not, but.
No, yeah, part of the reason I asked is because I've been and worked on projects that met that sort of trajectory of, it starts, it's in an RDBMS kind of very simple schema format, and it can support, you know, in the range of a couple 100 million records, barely. And then you start scaling and you start getting to the realm where that's doubled or tripled. And then suddenly things just start falling apart, and people go, oh, well, if we would have done it this way, we could have. But to your point, most of the time you don't ever make those transitions. It's almost too expensive to redo everything. You just figure out how to scale that small thing you need to do, or you redesign your schemas because it's easier that way.
Yeah, so I'd have to check, but I think most of the major databases support the ability to run in a duplicated or replicated form on something like AWS or Hadoop.
Mm-hmm.
And so basically what that means is that you're not getting MapReduce, but you probably don't care. What you're getting is you're getting, interestingly, a replication of the entire database, and then some front end that's deciding where it's going to shuttle the queries off to in order to actually solve them. And so you can push out the scalability of the database that way. It's a very non-granular solution, but it works really well actually. So, yeah.
Yep. Now, what we had to do is we wound up creating a very interesting partitioning strategy ourselves using SQL Server, so you can still do some very small amount of parallelization by the query optimizer.
Mm-hmm.
It's not to the same degree that Hadoop would do, but so yeah, I was just curious about that because that was something I had faced of, like, do we make this decision? It was kind of the thing we kept kicking it down the road of, do we migrate, and then we're like, well, we're stuck. Like, we can't do it now because there's so much data to move that we'll never do it.
Right. And I think that's your experience is pretty much the standard experience, is that migration is pretty rare. But what you might find is that if you started a new data warehouse, you might decide, well, we're going to do this one in Hadoop, right? We're not going to do this one in SQL Server. Or they might take a small project and try it just to see how it works. Most companies are really conservative, and so they don't want to change because the entire structure of everything is revolving around whatever technological solution they've chosen, right? All the programmers know how to program in that, all the hardware is designed for that, all the existing data lives in that, and if you want to share between that and something new, it's always a nightmare. So, yeah.
Cool. Thanks.
Okay. So let's talk about NoSQL. Huge buzzword, maybe not so much anymore because it's been a while, but still. And it's exactly what it sounds like. It's a non-SQL based approach to data storage and retrieval. And a lot of these things, so NoSQL is very hot. Right now, I think the hot thing would be deep learning or machine learning. But deep learning is just a subset of machine learning. It's a supervised machine learning strategy, deep neural networks. And they're very interesting. We work with them. But it's funny, so people always come along and they say, they said this about NoSQL, they say this about DNN. This is going to solve everything. And I'm like, And so my standard question is like, do we still have cancer? If we still have cancer, it's not solving everything. So let me know when you solve that, and then I'll give you a one-handed clap. And so the key is understanding what these things are and what they're good for, and then making a smart decision about when to use them and when not to. They can be super, super helpful, no doubt. For example, DNNs and computer vision have solved some problems that have been long-standing unsolvable problems for 20 to 30 years. Okay, they're also completely uninterpretable, like any neural network. And so in certain environments like banks, insurance companies, and other things, they're not usable because the regulators wouldn't allow that. And so the two areas I heard right now that are really hot in deep learning are, one is interpretability, being able to actually tell me how this thing is making its decisions, not just some black box that comes out with an answer. And the other, interestingly, is security, which is something I didn't think much about. But what they said is that if you can get into a deep learning model without me knowing it and slightly tweak the model, you can make it start giving like really wrong answers. It doesn't take much. And of course, since it's uninterpretable, I'm just going to assume that it's working as well as it worked when I tested it. And so those two areas are two areas that people are working very hard on. How can you set up a model so that slight tweaks don't completely blow it up? And then how can you know whether it's actually doing what it's supposed to be doing or not? But not talking about deep learning right now, NoSQL. And so really to talk about this, we have to start with, again, RDBMS. So you remember when we talked about these, This is Edgar Pond, relational algebra. That's what these are all built on. And they were proposed by IBM in the early 70s. And it was SQL initially. Structured English query language. And then I think that's why I always say SQL and not SQL. I don't know what other people use, but I call it SQL. And first released by Oracle, which was at the time called Relational Software in 1979. So that's the sort of like to take a tour of the history. And so the definition of an RDBMS, well, there's lots, but most people agree on these things at least. So data is structured in relations. And these are tables consisting of rows and columns. So matrices, basically. Rows are records, columns are the attributes within the record. And then the second is that relational operators are provided to manipulate this tabular data. And those relational operators are built up on top of relational algebra. Okay. So currently you have MySQL, and I just remembered, of course, my brain doesn't work very well, but this is what I use. MariaDB is an exact sort of replication, by and large, of MySQL, but it's open source. And again, the people are worried about MySQL only because Oracle owns it, and it's still open source, but they couldn't make it not open source at any point. And Oracle, Larry Ellison is a bit of a wackadoo, so he could do that. DB2, still very popular. Informix, those are both from IBM. SQL Server, that's Microsoft. Sybase, that's SAP. Okay. So there's tons of these out there. And so what a NoSQL server does is it doesn't use relational foundations. And there would be reasons why it doesn't do that. Okay. And those reasons should be good because the relational foundation is old and well tested, and it works really well on most problems, and more importantly, it's pretty battle tested. So it's unlikely that any one of these commercial databases is going to screw you over. But believe me, some of these new databases, which haven't had the time that these others have had to work out all the kinks, could cause you problems. Okay. Always back up, but I mean, I'm sure you do that, right? Because, yeah. So, what I was asked about is graph databases, and these are really interesting, actually. So these are specifically designed to store and retrieve a graph, a no-link graph structure. So you understand most graphs are described as nodes, and then relationships between the nodes, which are defined by edges or links. And so these don't necessarily work well in a relational database structure, even though it's not hard to put them in. Okay. So if you wonder, so what are these? DEX is one graph database. HyperGraphDB is another one. And then Neo4j, which is what we're going to talk about. And that was 2010 when Neo4j came out. And I think that Neo4j is probably the de facto standard for a graph database at this point. Although don't quote me on that, because this is not really, graph theory is something I understand, but graph theory is not an area I work in. And so I know Neo4j is one of the major graph databases. I don't know if it's now the de facto. Okay. So graph databases claim a number of advantages over your typical relational database. Okay. In particular, they're faster for associative data sets. They represent discrete, independent entities and relationships between entities. That's what an associative data set is, and you can see that, well, that exactly mirrors what a graph database is. So the entities are nodes and the relationships are the edges. Okay. Now, the key way that this is actually provided is that native graph databases implement what's called index-free adjacency. And sort of, from my perspective, this is the key to why these are faster. And it's also the case that index-free adjacency is really only ever going to be useful in things like associative data sets that represent graphs. So if you're doing stuff with graphs, then index-free adjacency is going to be a big win. If you're doing stuff that doesn't involve graphs, it's not. Okay, it's going to be a big kick in the head, actually. So this is where each node explicitly references its adjacent neighbor nodes. And does not need to use an index to find them. Okay, so what it means in graph terms is that when you look at a node structure inside something like Neo4j, part of that node structure is explicit references to the neighbor nodes that you're connected to by edges. So you never need to use any kind of indexing to find those neighbor nodes. You just look at the node and it'll tell you who its neighbors are. Okay? Whereas in a relational database, we can set that up, but you understand that relational databases often get a lot of their performance improvement through indexing. Okay? And so you might wonder, why is that useful? Why does that work well in the database of graph information? And so one of the things to think about is, well, think about what are you going to want to do with the graph database? You're going to want to run graph algorithms. algorithms, right? Like minimum spanning tree, shortest path, you know, other things like that. Okay, I could list off all these graph algorithms. So for almost any graph algorithm that you run, like minimum spanning trees is Dijkstra's algorithm, and it sort of walks out from some starting position until it touches all the nodes that exist in the graph, and it guarantees that there's a path between any node and any other node, and then every edge has a weight, and it guarantees that whatever tree it's built to give you that guaranteed coverage. If you sum up the weights on the edges, it's smaller than any other tree that you could produce. It also gives you that coverage. So it's a minimum tree that spans the nodes in the graph, okay? And other algorithms like shortest path, et cetera, they all involve walking around in the graph and trying to figure out, okay, what's the solution to this problem? And I think that's the key, is the walking part. You're almost always doing path searches or path extensions or other things like that when you work with graphs. And so it's never the case that you normally want to take a node and then jump to some node way far away in the database in one step. You always walk there over edges. And since all the algorithms are walking over edges, then this index-free adjacency sounds really useful, because from any node, the most likely thing you're going to want to do, in fact, maybe the only thing you're ever going to want to do, is know who your neighbors are and know what it costs to get to each neighbor. And then once you have those neighbors, you might do that again and again and again and again. But those neighbors are themselves going to have explicit links to their neighbors, and so that's going to be very cheap, right? As opposed to a relational structure, which you can set up, but then you'll get into this, you'll get into basically what's called I think this is where we see the join bomb, but you'll get into a situation where you start doing multiple joins, and it becomes very, very expensive in the relational algebra structure to actually do these kinds of things, okay? So I just want to emphasize, the reason I'm spending so much time on this, I just want to emphasize that adjacency-free indexing, if you remember nothing about graph databases, that's the key property that they provide that makes them faster for graph algorithms, okay? Any algorithm that doesn't do path type walking through a neighborhood from neighbor to neighbor obviously is not going to benefit from the fact that any entity has explicit references to its immediately neighboring entities, okay? And so in those cases, adjacency-free indexing is probably not going to be useful for them. Yeah. Does that make sense? Are there any questions about that? So the real question at this point then is, well, how does Neo4j provide that? And so what I'm going to have to do is I'm going to have to actually show you in fairly explicit detail the underlying structure of a node structure, like how Neo4j stores a node, and then how it does its explicit referencing to other nodes. And then you'll see, oh, I get it. I can see how you can be really fast about running around and finding all the neighbors or neighbors of neighbors or neighbors of neighbors of neighbors, and then doing this path search to try to figure out how to solve these problems. Okay. Any questions about that? Any questions about anything? Assignment? What you're going to do this summer? All right. I will let you go for today. And when we come back on Friday for our last class, we will finish our discussion in Neo4j. And I can answer any other questions you have then. All right. Thank you very much.
Thank you.
Thanks, guys.
Have a good day.